Hello everyone, my name is Luciana Asti and I'm here to present the work that I've done with Roberta Gori and Paolo Milazzo about a formal characterization and efficient verification of a biological robustness property. I basically divided my talk in three parts. In the first part, I will give you some background information about chemical reaction network and robustness property. Then, in the second part, I will show you how to use linear temporal logic to define this biological property, namely the robustness. And finally, I will show you on a real example, that is the ERK signaling pathway, how we can use monotonicity and the formal notion of robustness to reduce the computational effort of simulation that we need to study the dynamical behavior of biological system. As you may know, a cell is a very complex system because all the internal and external behavior are governed by a long series of chemical reactions that govern the basic cell's activities. We can imagine the chemical reactions as a chemical equation in which on the left we have the reactants that are the species that are consumed and that are transformed in other species that are the products of the chemical transformation that are created by this chemical transformation. And we can use different approaches to study the dynamical behavior of system. In our context, we use a deterministic approach, so we use the law of mass action, for which we can state that the reaction rate is proportional to the reactant's product. This means that for each chemical species involved in the reaction network, we have a differential equation that are written considering the processes in which the chemical species is consumed and the processes in which the chemical species is produced by the chemical transformations. In this context, we study a particular property of biological system, that is the robustness property, for which a system can be considered robust if despite the presence of internal and external perturbation, can maintain its functionalities. For example, if we imagine to observe a cell here, for example, if this cell is affected by external perturbation, we can state that this cell is robust if, for example, it can adapt itself to this new environment, or if it can work despite the presence of perturbations. There are many works about the robustness property, and the work that we consider for the formal definition of this property is the work done by Rizk. That expresses the robustness as the distance between a particular behavior of the perturbed system, given as a numerical time trace, and the expected reference behavior expressed by a temporal logic formula. So, if for example we consider this plot here, we can study the variation of the concentration of a protein B, and we can express its variation over the time using a numerical trace, that is a finite sequence of tuples describing system evolution with time. So we consider the increasing time points of simulation, the state variables, and the derivative of the variables. So for example here we have this numerical trace that represents exactly the evolution of the concentration of the protein B over time. And to express a particular property, they use the temporal logic formula, and so the logic operator to express if and when a particular property holds on a trace T. So in this case, if we consider the formula phi, we can say that at some point during this simulation, the concentration of the protein B is greater than 7. That is true since the concentration of B starts at 2 and goes to 10. To give us the notion of robustness, they start this work giving us other two important definitions. The first one is the violation degree, that is a notion to quantify how far from satisfaction a system's behavior is. So we have a formula phi that describes a property, and we can define the domain of the system, that is the set of values for which the formula phi that we are considering holds on the trace T. So for example, if we have here a formula phi that states that at some point the concentration of B is lower than 10 and greater than 2, we can define the domain of the system. In this case, for example, since the formula phi1 is equal to the domain that we have here, we can compute the difference, and we can say that is 0 since the formula phi is the same of the domain. If instead we consider another formula, like this one we are considering phi2, we can compute the difference since this formula is not really true considering this trace. So the Euclidean distance between the formula and the domain is equal to 2. From the violation degree, they derive the notion of satisfaction degree that define how good the perturbed system performs. So violation degree and satisfaction degree are more or less the same notion, but the satisfaction degree is a positive way to consider how the system behaves on considering with respect to the perturbations. In this case, for example, if we consider again the formula phi1 that has a violation degree with respect to the time trace equal to 0, we can notice that the satisfaction degree reaches the highest values because the domain and the formula are the same, so the satisfaction degree is maximum. Otherwise, for example, consider again a formula that is far from the time trace, so we can find a different satisfaction degree, and in this case the lower value is 0. From the satisfaction degree, they define the notion of robustness that can describe on average how the system behaves under perturbation. So we here consider many perturbations, and each of them can have a different weight and a different effect on the time trace that represent the system behavior. But a particular notion of robustness is the initial concentration robustness that studies the influence of perturbation of the initial concentration of species on the steady state of the system. If, for example, we consider this example that we have here a simple chemical reaction network, in this case we can study if changing the initial concentration of some chemical species that are involved in the network, we can verify if this perturbation can affect the system behavior at the steady state, considering the concentration at the steady state of other species that we call output. Looking at this example here, the input of the chemical reaction network is the species S, so we change the initial concentration of the species S and we verify what happens to the concentration of another species, that is the output P, at the equilibrium. To do that, we give a new formal definition of initial concentration robustness that is more particular with respect to the definition given by RISC. Because in that case their framework is very general, because they can study all the kinds of robustness. Instead, in our case, we want to focus on a particular definition of robustness, that is the initial concentration robustness. To give this formal definition, we use the formal language of continuous Petri net, that is the advantage to give us also a graphical representation of the dynamical behavior of the system. To build the Petri net, we associate to each species involved in the chemical reaction network a circle, that is a place, that is characterized by an initial concentration, and we associate to each chemical transformation a transition, that is another kind of node that is represented by a square and which represents in this case the chemical transformation. And to each chemical species we associate a value which represents the initial concentration. To the input, that is the particular species that is affected by the perturbation, we associate an interval of values, like in this case. So for example, for S, that is the species that we want to perturb to study what happens to the steady state of the output, that is P, we associate an interval of possible values, and we verify if at the steady state the concentration of the output species is within a range. If it is the case, we compute the alpha, that is the range of the interval that we found at the steady state for the output P. So this is our alpha, which represents how the perturbation affects the steady state of the system, considering a particular species that is the output. But as I already mentioned before, our definition is particular with respect to the definition given by RISC. So we adapt the framework of RISC to study the initial concentration robustness, and so we rewrite the formula of the robustness given a particular formula phi that we want to verify on the time trace of the simulation. For us, as already said before, the output, the concentration of the output at the steady state, so at some point globally the concentration of the output at the steady state has to be within a range. So in this case, if we consider again the example that I showed you before, we change the initial concentration of S, that is our input, and we verify by simulation if the concentration of the output is within a range, as expressed by our formula phi. But to verify our definition, we use many simulation as RISC, but the problem is that also if we consider only the perturbation that can affect the initial concentration of the input, we have to deal with many simulations, so a very high computational effort. The main advantages to use our approach is that for a particular class of chemical reaction network, we can use combined with our approach, the alpha robustness, we can use the monotonicity properties to reduce the computational effort of simulation. I show you on example what is the approach. In particular, the approach is quite nice because the idea is that if the output is monotonic with respect to the initial concentration of the input, we can avoid to do all the simulations. Indeed, for example, in this case, to verify how the concentration of the output reacts to the perturbation of the initial concentration of the input, we have to do many simulations because, for example, in this plot we change the initial concentration of the input and we verify that at the steady state the concentration of the output increases. But if we can state that the output is monotonic, we can avoid all the possible simulation and do, for example, only the two simulations, one for the minimum value of the range and the other one for the maximum value of the range. Using the monotonicity, we can do this approach. For example, on the larger example of ERK signaling pathway, it is possible. This ERK pathway is a very important chemical reaction network because it is involved in many biological phenomena such as cell growth and differentiation. As you can see, we build the Petri nets of the chemical reaction network and we identify the two species that we want to study. In this case, the input is the species RAF and the output is the species PPMA-K1. And also in this case, to study what happens at the steady state of the system, we have to perform many simulations, as you can see here. So on the horizontal axis, as before, we plot the initial concentration of the input, and on the vertical axis, we plot the value of the steady state of the concentration of the output. But since we can apply in this case some monotonicity result that we can use to state that the output is positively monotonic with respect to the input, we can do just two simulations because we already know that changing the concentration of our input, we obtain that the concentration of the output at the steady state increases. So, for example, in these simulation results, we can consider one simulation for RAF equal to 1 and one simulation for RAF equal to 100. And so we find exactly that the concentration of the output increases. So, using this approach, we need only two simulations and we can drastically reduce the computational effort of simulations. Thank you very much and time for questions.
So, welcome back to the Q&A session for third paper of this session. And then there's currently only one question, so please write a question in the chat if you have any other questions. So my question is basically, it seems that according to the presentation, your paper, there's already robustness property, and you have defined initial concentration robustness property. So I'm wondering why that is quite important for biological systems. That's probably your domain, right? So
yeah, thank you for the question. And as you can see, my presentation in general is quite difficult to have a general formalization of robustness, since you can take in account different properties, like, for example, you can have perturbation on the chemical reaction network concentration, or maybe in the rates. And so the work done by Risk and the other authors are more related on give a general definition of robustness. In our case, we can study initial concentration robustness because it's the most common problem in particular disease like cancer, since, for example, when you have a chemical reaction network, when you change the initial concentration of the species, you are changing also the initial condition of the ODEs that you can use to study the network. And many different work in vitro shows that this is the most important problem when we are dealing with the cancer or other disease. Also, when you want to study, for example, the signaling pathway that are particularly common in enzyme chemical reaction networks.
Oh, I see. That's a really important property.
Yeah, but of course you can also study different notion. We decide for this one because it's quite important also for biological field, and so we use this one. But you can also restrict your attention to other particular notion of robustness.
Good. Thank you for answer. Oh, there's another question. Thank you. So from Laura, can the monotonicity assumption applies to other biosystems and in case to other domains?
Yeah, we use monotonicity in particular to reduce the computational effort of simulation. So in our case, we can reduce the number of simulation because we restrict the number of simulation only on the intervals of the initial concentration. So we pick, for example, the minimum on the maximum of the interval of the initial concentration. For in our case, we can use monotonicity in this way. But if we want to study other particular properties of biological field, we can study also monotonicity, for example, to in signaling processing, or for example in structural biology, you can use monotonicity to build fake chemical reaction network, because you can use modularity, and so build chemical reaction network that are that have this property. And so yeah, you can also use for other task. But in our case, the idea was only to restrict reduce the number of simulations.
So actually, I also curious related to. Oh, by the way, there's another question. Probably should be first. So by Simon, is there a way of validating your approach against real biological systems? Complex?
The idea is that we test our monotonicity procedure on a huge dataset that is biomodel dataset, and using this approach on complex networks, we realize that in our case we can really reduce the number of simulation, because we can imagine a really big chemical reaction network, and instead to test all the possible parameters, we can now just have 1 or 2 simulations, because if this property holds on our system, we can also don't do simulation, since we know that this property is true for the chemical reaction network. And yeah, the simulations are very complex because there are many factors that we have to consider when we do simulation, since we have to consider temperature, pressure for chemical reaction in the real world. So our validation is that we can compare our result with the real database that we found in so biomodels is one of them, for example.
I see. So actually related to this question, so how common this kind of this monotonicity assumption hold in chemical reaction network? So is it kind of common to have that property, or?
Since the networks are very complex and the monotonicity is a very strict condition, we cannot use in general on all the chemical reaction network. But one of the possible approach is, for example, to take the chemical reaction network and subdivide in small networks to test our condition on subnetworks. And so this is why is an idea. for example, and it is quite useful because in this way you can restrict your investigation. And because sometimes it happens that our condition is very strict, so you cannot apply it directly on a big networks. On the another idea we are working right now is, for example, to use other condition together with our definition. And for example, we can use some information from separation of time scale, or reducing the dimension of the network, apply other notion. For example, the complex balancing networks, for example, you can rewrite the system and obtain a smaller system that you can use to verify the same network, because they are equivalent. So we can use different approaches to apply our condition.
I see. So what would be the source of biological systems? PubMed? What kind of that? So source of, so how did you develop or obtain this biological model?
There are many approaches. One, for example, is to have directly the data from experiments, for example. And there are some biologists that work with us, for example, that they reconstruct the network. This is one of the approach. Or, for example, you can use different computational methods. Like, for example, one of idea is to use sensitivity analysis to check the parameters. So, for example, you have some data, and then you can work on it to find the network. But it's not so easy, since they are very, very complex. For the same condition that I already said before, like, for example, the pressure, temperature, and so on. So we can also use other formal methods, for example, Boolean network, that are very common to build the network of real data from this field.
Oh, I see. Thank you.
You're welcome.
Yeah, so we have 2 minutes left, so probably I may give one more question. So I guess that kind of simulation seems to quite center of your actual tool, right, or computation method. So I guess there's many simulation methods actually. So do you have any specific restriction or assumption caused by certain simulation method, or not so much? So like the ODE, or given ODE may have some constraint, I guess, probably.
From a deterministic point of view, we can use the ODE, so they have no condition, particular constraint on the modelization. You change the initial concentration. For example, you can text the work, the simulation of the real networks. And and this is one of the possible approach. Otherwise, you can also use a stochastic point of view. And in that case, it be a little bit more complex, because since we are dealing with a sort of you have a lot of particles that you have to model. So in that case, it's a little bit more difficult. But it depends on on what you want to study. In our case, since we want to have a sort of approximate behavior of the network, in our case, we can work on it with deterministic modelization. Because in this way you have a macroscopic study of the network. Otherwise, if you want to studying exactly what happens in a cell, for example, in that case, I suggest to use another kind of simulation, like, for example, Monte Carlo.
I see. Oh, so one more question. So could your approach be adapted to system with discrete events? So additional catalyst. Okay.
Yeah, because when you build the simulation, you can also add some particular events, like, for example, the injection of other particles in the system. In our